Imagine the impossible. Just imagine for a moment that we could travel faster than light, not in science fiction, not in a dream, but in reality. For centuries, humanity has been bound by the speed of light, a cosmic speed limit that seemed unbreakable. But recent discoveries in physics, cosmology, and quantum theory suggest that the rules may not be as rigid as we once thought. What if the stars, the galaxies, and even other universes could be within our reach if only we understood how to manipulate space itself? Today, I want to take you on a journey through the mind-bending possibility of faster-than-light travel, exploring what science says, what theory allows, and what humanity may one day achieve. That for centuries humanity has been bound by the notion that nothing can exceed the speed of light. This limitation, embedded in the framework of Einstein's theory of relativity, has defined the boundaries of physics as we understand them. Light is not merely a measurement of speed, it is the ultimate cosmic speed limit, a law of nature that dictates how matter, energy, and information propagate throughout the universe. Every satellite, spacecraft, and interstellar probe has been designed with this constraint in mind, and our understanding of space-time has been shaped by the fact that travel beyond this speed was considered impossible. Yet, as we probe deeper into the structure of the cosmos and refine our mathematical understanding of relativity, we begin to recognize that this speed limit applies only in conventional space-time. While no object with mass can move faster than light through normal space, the fabric of space itself is not bound in the same way. Space-time is a flexible, dynamic entity capable of stretching, contracting, and warping under the influence of energy and gravity. This opens the door to possibilities that were once thought to be pure fantasy. If we can manipulate space itself, then the distance between the points can be shortened without violating the local speed limit. In other words, the universe may permit a form of faster-than-light travel, not by moving faster through space, but by moving space itself around a vessel, effectively creating a shortcut through the cosmic fabric. This subtle but profound distinction transforms our understanding of interstellar travel. Rather than imagining a spacecraft as a rocket propelling itself against the vacuum of space, we can begin to envision it as a passenger riding on a moving segment of space-time. In this scenario, the ship does not locally exceed the speed of light, preserving the laws of relativity, but it is carried across cosmic distances much faster than light would traverse the same region of unaltered space. This idea is not merely a flight of fancy, it emerges from rigorous solutions to Einstein's equations. The theoretical possibility of manipulating space-time challenges our traditional notions of movement, distance, and causality. It forces us to reconsider what is truly impossible in the universe. The implications extend far beyond interstellar travel. They invite us to rethink energy, matter, and the very nature of reality. Once humans accept that space can be engineered or manipulated, the first step toward traveling faster than light shifts from defiance of natural law to the mastery of cosmic geometry. Central to this concept is the realization that faster than light travel is fundamentally a problem of geometry and physics rather than raw propulsion. The universe is vast, and the distances separating stars are enormous, measured in light years that stretch human imagination. Under conventional propulsion, these distances are insurmountable within a human lifespan. Even our most advanced chemical rockets, ion drives, or nuclear engines would require decades, centuries, or millennia to traverse interstellar space. But if we can warp space itself, contracting it in front of a vessel and expanding it behind, or traversing stable wormholes, connecting distant points of the cosmos becomes far more navigable. Distances that once appeared absolute can be modified through the manipulation of space-time. This realization reframes exploration not as a race against time, but as a challenge in mastering the structure of the universe itself. It transforms the problem of interstellar travel from brute force engineering into an elegant question of physics, geometry, and energy distribution. The concept of wormholes exemplifies this approach. A wormhole can be envisioned as a tunnel connecting 2 points in space-time, reducing what would be an immense journey to a near instantaneous traverse. While wormholes remain hypothetical, their existence is permitted by the equations of general relativity. Stabilizing them, however, presents profound technical challenges. Exotic forms of matter, negative energy densities, and immense gravitational control are required to prevent such a tunnel from collapsing. Despite these obstacles, the very fact that mathematics allows for their possibility shifts the paradigm of interstellar travel. Transforms faster than light travel from the realm of imagination into a legitimate scientific question, not if it violates physics, but if it can be realized within the constraints of energy, material science, and advanced engineering. Once this mindset is adopted, the pursuit of such capabilities becomes a question of innovation and persistence rather than impossibility. The universe suddenly appears less like an immutable barrier and more like a landscape with hidden paths waiting for those capable of understanding and navigating its geometry. Equally important is the subtle insight that relativity governs local motion, not the expansion of space itself. Observations in cosmology reveal that galaxies recede from one another faster than light due to the expansion of the universe, a phenomenon that does not violate Einstein's laws. If space can naturally expand and contract on cosmic scales, the engineered manipulation of the same principles may enable faster than light transit. This insight encourages a reimagining of spacecraft design, focusing not on achieving extreme local velocities, but on controlling and shaping the medium through which the craft moves. It shifts the challenge from brute mechanical acceleration to mastery of energy distribution, gravitation, and space-time geometry. The human mind, therefore, becomes the primary frontier, understanding the universe's structure in order to bend it to our purpose. The implications of these discoveries extend beyond physics and engineering into philosophy and imagination. For centuries, humans have looked at the stars and considered them untouchable, infinitely distant, and effectively unreachable. The recognition that the cosmos may be navigable on timescales relevant to human exploration transforms that perception. The stars are no longer merely symbols or distant lights. They are potential destinations, each with unique opportunities for discovery, observation, and eventual habitation. The knowledge that we might one day traverse the interstellar void in a practical time span inspires not just scientists and engineers, but society at large, catalyzing new ambitions, cultures, and priorities. Exploration becomes not a question of if, but how, and imagination becomes the first laboratory where the physics of possibility is tested. Understanding these principles also alters the way humanity approaches technological innovation. If faster than light travel is framed as the manipulation of space-time rather than the acceleration of matter, then the focus shifts to energy generation, space-time engineering, and control of exotic matter. Research into high-energy physics, gravitational fields, and quantum phenomena becomes not just theoretical curiosity, but directly relevant to the future of civilization. Every experiment in particle physics, every study of cosmic microwave background radiation, and every probe into black holes contributes pieces to the puzzle. The pursuit of faster-than-light travel becomes a grand synthesis of mathematics, physics, and engineering, demanding both intellectual creativity and precise technological execution. It is an endeavor that unites theory and application, imagination, and rigor, into a singular goal that has captivated human thought for generations. Equally important is the realization that human perception of distance and time is relative. While a star may lie light years away from Earth, manipulation of space-time could allow a spacecraft to reach it within a human lifetime. The notion of impossible distances is reframed entirely, allowing new planning for exploration, colonization, and observation. This changes the psychology of space exploration. What was once distant, dangerous, and unreachable becomes conceivable, manageable, and inspiring. Human ambition expands along with the potential paths through space, cultivating a generation of thinkers and engineers attuned to the reality that the cosmos is navigable not in a distant future, but as an eventual achievable goal. Finally, the first step toward faster-than-light travel begins in the mind. Understanding the universe's possibilities, imagining how space can be bent, and conceiving of technological solutions to seemingly insurmountable challenges is the precursor to any practical achievement. Before warp drives, wormholes, or space-time manipulation can be realized, humans must first accept that these concepts are consistent with the laws of physics, and then dedicate intellect, creativity, and energy toward their realization. Curiosity, combined with rigorous scientific inquiry, lays the groundwork for the eventual engineering breakthroughs that could make the dream of interstellar travel a reality. By daring to imagine the impossible, humanity positions itself to one day turn faster than light travel from theory into fact, expanding civilization beyond the limits of our current understanding and reaching into the vast expanse of the universe. The concept of a warp drive is perhaps one of the most fascinating and mind-expanding ideas in theoretical physics, and it represents a fundamental shift in how we think about faster-than-light travel. Unlike conventional propulsion, which relies on the application of force to push a spacecraft through space, a warp drive would manipulate the very fabric of space-time itself. By contracting space in front of the vessel and expanding it behind, the ship could effectively surf a wave of space, traveling vast interstellar distances without ever locally exceeding the speed of light. The brilliance of this concept lies in its subtle adherence to Einstein's relativity. The ship itself is not moving faster than light in its immediate vicinity, yet the overall journey covers enormous distances and timescales that would otherwise be impossible. While this idea has long been popularized in science fiction, recent theoretical work has demonstrated that it is consistent with the equations of general relativity. The challenge, of course, is practical. Constructing such a system would require exotic matter with negative energy density, precise manipulation of gravitational fields, and energy scales far beyond anything humanity can currently generate. Yet the fact that these concepts are mathematically possible shifts faster than light travel from impossible fantasy to theoretical plausibility. It challenges us to rethink not only the engineering problems, but also our philosophical understanding of movement, distance, and time. Warp drives open a realm of possibilities for the exploration of distant star systems. Under conventional propulsion, the nearest star system, Proxima Centauri, is over 4 light-years away, a journey that would take tens of thousands of years with current technology. A warp drive, by manipulating space-time, could compress that distance and allow a spacecraft to reach such a system in decades rather than millennia. This transforms our conception of interstellar travel from an impractical dream to a realistic objective, at least in principle. It also raises profound questions about energy, safety, and control. The manipulation of space-time is not a passive endeavor. The contraction and expansion of space involves extreme forces that, if uncontrolled, could have catastrophic consequences. Engineers and physicists would need to develop methods to stabilize and contain the energy fields, ensuring that the ship and its occupants are protected. Every solution in this field requires a combination of creativity, rigorous mathematics, and deep understanding of fundamental physics. Warp drives force us to confront the universe not as a static backdrop, but as a dynamic medium that can be shaped, molded, and utilized. The very nature of travel shifts from propulsion against resistance to engineering of space itself, redefining the limits of exploration. Equally compelling are wormholes, hypothetical tunnels connecting 2 distant points in space-time. Unlike a warp drive, which manipulates space around a vessel, a wormhole acts as a pre-existing shortcut through the cosmos. The theoretical framework for wormholes emerges from Einstein's general relativity, which allows for solutions where space-time is folded or curved in such a way that 2 distant points become adjacent in a higher dimensional sense. The notion of stepping into a tunnel on one side of the galaxy and emerging instantly on the other is no longer pure fantasy. It is a legitimate theoretical possibility. Stabilizing a wormhole, however, is a monumental challenge. The structure would naturally collapse with that exotic matter capable of producing negative energy density to hold it open. Such matter, though currently speculative, is permitted within quantum theory, suggesting that future advances in understanding and manipulating fundamental physics could make wormholes more than just theoretical constructs. If realized, they would transform space travel, allowing humanity to traverse vast interstellar distances instantaneously and redefining our understanding of connectivity and causality across the cosmos. The exploration of wormholes and warp drives is not just about engineering, it also forces us to rethink time and causality. Traveling through a wormhole could, in principle, allow a form of temporal displacement, raising questions about cause and effect, the nature of events, and the stability of the universe itself. These are not trivial philosophical concerns. They are critical constraints that any practical system would need to address. Advanced civilizations capable of faster-than-light travel must understand not only the manipulation of space-time, but also the consequences of doing so on the flow of time itself. This intertwining of physics, engineering, and philosophy underscores the profound implications of faster-than-light travel. It is a technology that challenges our understanding of reality at its most fundamental level, reshaping not only what is possible in terms of exploration, but also how we understand the nature of existence itself. The implications for human civilization are equally profound. With warp drives or wormholes, interstellar travel becomes feasible on timescales relevant to human lifespans. This changes the scope of ambition, strategy, and planning for humanity. Star systems that once appeared unreachable suddenly become potential destinations for exploration, colonization, and scientific observation. The challenges of survival, communication, and resource utilization extend beyond Earth, demanding new forms of governance, collaboration, and problem-solving. Multi-generational planning becomes central, as missions may span decades or centuries, requiring sophisticated social structures, psychological resilience, and technological continuity. Humanity must learn to think on cosmic scales, balancing immediate needs with interstellar ambitions, and developing ethical and practical frameworks for life beyond a single planet. Moreover, the study of warp drives and wormholes spurs innovation in other areas of science and engineering. Attempting to manipulate space-time, even theoretically, drives advances in high-energy physics, quantum mechanics, material science, and energy generation. Each theoretical breakthrough provides insights into more conventional technologies, from propulsion and energy storage to communication and autonomous systems. Research into the extreme requirements of faster-than-light travel cultivates a culture of problem-solving at the boundaries of human understanding, inspiring new generations of scientists and engineers to tackle the universe's most profound questions. The pursuit itself becomes a driver of human progress, regardless of whether practical implementation is achieved in the near term. These concepts also challenge our perception of scale, distance, and possibility. By demonstrating that space can be engineered, warped, and traversed in ways that bypass the conventional speed limit, warp drives and wormholes force humanity to rethink what is reachable. The cosmos ceases to be an unreachable backdrop and becomes an arena for practical exploration, scientific discovery, and eventually habitation. Every star, every galaxy, every system of planets becomes a potential laboratory for learning, adaptation, and civilization building. Imagination, guided by rigorous physics, becomes a crucial tool for expanding the frontier of human activity. The mind, not just technology, becomes the primary instrument of interstellar exploration. Finally, both warp drives and wormholes remind us that faster-than-light travel is ultimately a problem of integration, integrating physics, mathematics, engineering, and human vision into a coherent pursuit of possibility. It is not enough to understand a theory mathematically. Practical realization requires deep interdisciplinary work, technological innovation, and sustained imagination. These concepts challenge humans to grow intellectually, technologically, and culturally, demanding new forms of education, collaboration, and problem-solving. The pursuit of faster-than-light travel is therefore a journey not only into the cosmos, but also into the depths of human potential, reshaping what we believe is possible and inspiring generations to explore, innovate, and dream beyond the boundaries of our current understanding. Energy is the ultimate currency of the cosmos, and when we consider faster-than-light travel, it becomes clear that the challenge is not simply moving from one point to another, but mastering the immense energy scales required to manipulate space-time itself. To warp space or stabilize a wormhole, we are talking about energies that dwarf anything humanity has yet generated. Even the most powerful nuclear reactors and experimental fusion devices are infinitesimal compared to what would be required to bend the very fabric of the universe. This is not a problem that can be solved incrementally or through brute force. It demands a radical rethinking of energy generation, storage, and distribution. Humanity would need to tap into processes that rival the output of stars, perhaps through controlled fusion, antimatter reactions, or even the speculative zero-point energy predicted by quantum field theory. Each of these possibilities presents enormous technical challenges, from containment to conversion efficiency to safety, but the mathematics and physics suggest that such energy sources, while extraordinarily ambitious, are not fundamentally impossible. The question shifts from can it be done to how can we develop the technology and understanding to do it safely and effectively. Mastery of energy at this scale is not merely a technical requirement. It shapes every aspect of interstellar travel. The energy must be generated, controlled, and focused with extraordinary precision. Small deviations in a warp field or a wormhole stability could have catastrophic consequences, from collapsing the passage to producing radiation or gravitational anomalies that endanger both the spacecraft and its occupants. This imposes unprecedented demands on engineering, requiring innovations in field manipulation, feedback systems, and automated control mechanisms that operate faster and more accurately than human reflexes could manage. Advanced artificial intelligence is likely to play a central role, monitoring and adjusting energy flows in real time, ensuring stability and compensating for cosmic perturbations. In this way, the challenge of energy becomes a driver of technological sophistication across multiple domains, pushing humans to develop systems that are as intelligent as they are powerful. The link between energy and faster-than-light travel also illuminates the fundamental limits and possibilities of physics. Einstein's equations describe not only the speed of light limit, but also the relationships between mass, energy, and space-time curvature. To manipulate space on cosmic scales, one must engage with the deepest principles of the universe. The energy required to create a stable wormhole, for example, may involve not only raw power, but precise shaping of exotic matter with negative energy density. Similarly, sustaining a warp bubble demands continuous energy management to maintain the contraction and expansion of space in perfect equilibrium. These are not trivial problems. They sit at the intersection of theoretical physics, engineering, and cosmic scale resource management. Yet the fact that equations allow these possibilities is profoundly inspiring. It suggests that energy, intelligence, and human ingenuity are the true keys to transcending the barriers of conventional space travel. Relativity introduces a second layer of complexity, the interconnection of space and time. Moving near the speed of light stretches and warps time, a phenomenon known as time dilation, in which a traveler experiences time differently from observers at rest. Faster than light travel, if achieved through manipulation of space-time, introduces even more complex temporal effects. Traversing a wormhole or riding a warp bubble could allow what appears to be instantaneous travel across light years, but it could also challenge causality, raising questions about the sequence of events and the fundamental order of the universe. These are not abstract concerns. Any practical implementation must account for the temporal consequences of manipulating space itself. Engineers and physicists must understand how energy and space-time curvature interact to ensure that faster-than-light travel does not produce paradoxes or instabilities that could endanger the mission or alter the timeline in unforeseen ways. Mastery of energy is therefore inseparable from mastery of the temporal structure of the universe. Beyond the technical challenges, these concepts redefine humanity's relationship with the cosmos. If energy can be harnessed to manipulate space and time, then the universe is no longer an unreachable expanse of light years and impossibilities. Star systems, galaxies, and even distant clusters become accessible, not in centuries or millennia, but in decades or potentially years. The psychological impact of such a realization is profound. What was once awe-inspiring and untouchable becomes tangible and reachable. The human mind is forced to expand its conception of possibilities, stretching imagination to match the scale of the universe itself. Energy, in this context, is not just a physical requirement. It becomes a measure of ambition, a test of ingenuity, and a gateway to exploration. The civilization capable of generating, controlling, and applying such energy is not merely technologically advanced. It is conceptually evolved, capable of thinking and planning on cosmic scales. The requirement for immense energy also drives interdisciplinary innovation. Efforts to harness fusion, antimatter, or zero-point energy intersect with advances in material science, quantum physics, and artificial intelligence. Each breakthrough in energy generation or control has ripple effects, enabling other technologies necessary for our interstellar exploration, life support, radiation shielding, navigation systems, and propulsion. The pursuit of faster-than-light travel thus catalyzes a cascade of scientific and engineering developments, each feeding into the next. It is a grand synthesis where energy, intelligence, and creativity converge to expand the horizons of what humanity can achieve. This integration demonstrates that energy is not just a fuel. It is the medium through which civilization grows, explores, and ultimately transcends its planetary origins. Finally, the consideration of relativity and energy together highlights the profound philosophical implications of faster-than-light travel. Time, distance, and causality are no longer immutable. They are elements of a flexible cosmic framework that can be shaped and navigated with sufficient understanding and power. Human ambition is no longer constrained to the familiar scales of Earth or the solar system. It extends into the galaxy and beyond. The pursuit of faster-than-light travel is therefore a pursuit of knowledge, courage, and imagination at the largest possible scale. Every theoretical advance, every experiment in energy manipulation, and every step toward understanding space-time brings humanity closer to the dream of interstellar exploration. It is a journey not only across distance, but across the limits of thought itself, expanding the realm of what is possible and inspiring generations to come to reach for the stars with intellect, creativity, and vision. When contemplating the vastness of the cosmos, one of the most profound realizations is that faster-than-light travel is not merely a technical challenge. It is a transformative force that could redefine the trajectory of human civilization. If humanity were able to traverse the stars at speeds that defy conventional understanding, the implications would ripple through every aspect of our culture, technology, and identity. The ability to reach other star systems within a human lifetime would fundamentally alter how we think about exploration, resource allocation, and our very place in the universe. For millennia, humanity has been confined to a single planet, viewing the stars as distant, untouchable points of light. Each step beyond Earth, from the first satellites to the moon landing, expanded our perspective. But the solar system itself represents only a tiny fraction of the galaxy. Faster-than-light travel would shatter these boundaries, transforming distant points of light into tangible destinations. Civilizations would no longer be bound by the slow pace of conventional propulsion or the tyranny of light years. Instead, the galaxy itself would become a navigable terrain, offering opportunities for exploration, habitation, and discovery that were once the exclusive domain of imagination and science fiction. This expansion would not be trivial. It would require humanity to think on cosmic scales, to plan across generations, and to develop technologies capable of sustaining life and culture across unimaginable distances. In this sense, faster-than-light travel is not merely a scientific endeavor. It is a civilizational leap, a bridge between our current understanding and a future in which humanity participates fully in the galaxy. The expansion into interstellar space would also catalyze unprecedented cultural and philosophical evolution. Societies living on multiple planets or traveling between stars would confront challenges that demand unity, collaboration, and long-term thinking. National borders and political divisions, so critical to life on Earth, would pale in comparison to the necessity of cooperation across interstellar distances. Resources, communication, and decision-making would require a level of coordination and trust unprecedented in human history. These conditions would foster new forms of governance, ethics, and social structures, emphasizing shared responsibility, foresight, and adaptability. The very concept of civilization would be transformed. It would no longer be Earth-centric but interstellar in scope, bound not by geography but by shared ambition and mutual dependence. Humanity's cultural evolution would accelerate as societies learn to manage the psychological, logistical, and ethical complexities of living across the stars. Children growing up in this context would inherit a worldview that is fundamentally different from ours, one in which the galaxy itself is a familiar environment, not a distant abstraction. This transformation would extend beyond mere survival or convenience. It would reshape the way humans perceive time, space, and the responsibilities that come with intelligence and consciousness. Faster than light travel, therefore, is not only a technical possibility, but a catalyst for the evolution of human thought and society itself. Equally transformative is the effect of such capabilities on the pace of scientific discovery. If star systems become accessible within human lifetimes, the accumulation of knowledge accelerates exponentially. Every planet, moon, or asteroid visited provides data that informs the next mission. Observations of alien geology, atmospheres, radiation patterns, and potential life forms would revolutionize multiple scientific fields simultaneously, from biology and chemistry to astrophysics and cosmology. The feedback loop between exploration and discovery creates a self-reinforcing cycle. Greater knowledge enables more ambitious missions, which in turn generate even more data, expanding both our understanding and our capacity for technological innovation. The combination of faster-than-light travel and sophisticated data analysis would allow humans to investigate phenomena that were previously inaccessible, from the life cycles of distant stars to the composition of exoplanetary ecosystems. In essence, this capability would convert the galaxy into an immense, interconnected laboratory where every mission advances both practical capability and fundamental knowledge. The very process of exploration becomes a tool for education, inspiring successive generations of scientists, engineers, and thinkers to push the boundaries of what is possible. The psychological impact of faster-than-light travel is equally profound. Humans are accustomed to thinking in terms of familiar distances, daily rhythms, and the timescales imposed by conventional travel. Expanding our reach to other stars challenges these intuitions, requiring new cognitive frameworks for understanding distance, time, and causality. Travelers moving between star systems would need to adapt to environments in which isolation, delayed communication, and extreme conditions are routine. The development of resilience, adaptability, and interstellar collaboration would not be optional but essential. This psychological adaptation extends to civilization as a whole. Societies capable of sustaining multi-generational interstellar missions would cultivate patience, long-term planning, and strategic thinking on scales far beyond what is required on Earth. The human mind would evolve alongside technological capability, learning to integrate knowledge, intuition, and foresight to navigate a galaxy that is simultaneously vast and intimately accessible. In this way, faster-than-light travel is not just a technological milestone, it is a cognitive and cultural one, expanding both human capability and understanding. The integration of technology, psychology, and culture also reshapes human identity. Life in a multi-planet or interstellar civilization challenges traditional notions of home, nationality, and community. Humans would become citizens not of a single planet, but of a galaxy, with identity increasingly defined by adaptability, curiosity, and collaboration. The boundaries of what it means to be human would expand, incorporating the capacity to survive, thrive, and innovate in environments radically different from Earth. Artificial intelligence, autonomous habitats, and sophisticated life support systems would extend the reach of human cognition and capability, enabling explorers to operate safely and effectively in extreme conditions. This synergy between biological and technological intelligence transforms exploration into an integrated enterprise where humans, machines, and the environment interact dynamically to support life and discovery. Faster than light travel thus becomes a crucible for the evolution of human identity, creativity, and societal organization. Another critical aspect of this expansion is the redefinition of energy and resource management. Faster than light travel demands energy on scales that dwarf anything currently produced on Earth, requiring advances in fusion, antimatter, and potentially speculative forms of zero-point energy. Managing such energy safely and efficiently becomes a central concern, shaping not only propulsion and navigation, but also habitat design, life support, and long-term sustainability. The pursuit of these capabilities fosters innovation across multiple disciplines, from high-energy physics to material science and artificial intelligence. Each breakthrough reinforces others, creating a compounding effect that accelerates the pace of technological and scientific progress. The quest for faster-than-light travel thus acts as a catalyst, driving the development of infrastructure, expertise, and understanding that benefits all aspects of human civilization. Ultimately, faster-than-light travel is not merely a technical or scientific achievement, it is a transformative force that reshapes humanity's destiny. The ability to traverse the stars within human lifetimes expands our conceptual horizons, accelerates the acquisition of knowledge, and drives cultural and psychological evolution. Civilizations capable of such travel think on scales far beyond the planet, coordinating resources, knowledge, and ethics across light years. Each mission, each technological advance, and each cognitive adaptation compounds the potential for discovery and expansion. The universe, once an intimidating void, becomes a landscape for human creativity, exploration, and civilization building. Faster than light travel thus embodies not only the ultimate challenge of physics, but also the ultimate expression of human curiosity, ingenuity, and ambition. The stars are no longer distant points of light. They are destinations, laboratories, and catalysts for the evolution of both civilization and consciousness. As we reflect on the possibilities of faster-than-light travel, it becomes clear that this is not just a question of rockets. Energy or engineering it is a question of humanity's imagination, courage, and vision. The ability to traverse the stars would transform civilization, expand our knowledge, and redefine what it means to be human. Distances that once seemed insurmountable could be crossed, new worlds could be explored, and the very fabric of space and time could become a medium for discovery. This journey challenges us to think on cosmic scales, to master energy, to innovate with intelligence, and to evolve culturally, psychologically, and philosophically. Faster-than-light travel represents the ultimate frontier, not only of science, but of human potential. Thank you for joining me on this journey of exploration and imagination. Your curiosity, passion, and willingness to dream alongside science are what propel us toward the stars. Together, we continue to push the boundaries of knowledge and step boldly into the vast, magnificent universe that awaits.